So in the previous lecture, we discussed that there are two major sources of non-determinism in the semantics of concurrent programs. The one is the thread interleaving. The execution of multiple threads are interleaved with each other, and the order of the execution introduces non-determinism. And the other major source of non-determinism is the reordering. Inside a thread, multiple instructions may be reordered, resulting in what is called relaxed behaviors. That would be impossible with only interleaving semantics, but made possible by the reorderings. And in the previous lecture, we also discussed that we need to find the semantics, the good semantics for such relaxed behaviors, in order to reason about the concurrent programs. So in this lecture, we are going to study what is called promising semantics, which is, I believe, the best of its kind and the state-of-the-art semantics for concurrent programs. So this is actually made by me, and 3 years ago, I published a paper that's called Promising Semantics for Relaxed Memory Concurrency, which defines the relaxed memory concurrency semantics for C and C++ or Rust programs. So let me tell you a little bit more about this promising semantics, because each semantics will be the basis for all the constructions of concurrent objects, including logs or data structures or some garbage collectors. And in the design of such concurrent object, we are going to use these semantics to reason about the correctness of those concurrent objects. So at the high level, the promising semantics is also an interleaving operational semantics. The threads are executed one at a time, and each thread has turn. So it is an interleaving semantics. So the good story is that the good news is that it is still not that crazy difficult. It is interleaving. It is just expected from the nature of the concurrent programs. But the bad news is that in order to model relaxed behaviors and ordering, it is a little bit more difficult than what is called sequentially consistent semantics, where the threads are only executing for just plain memory and just plain program. In order to track the relaxed behaviors and ordering, so it introduces a few ideas that is listed here. There are 4 key ideas. The first key idea of promising semantics is that it uses the memory that is a little bit more complicated than the sequential memory. In the sequential memory, memory is just the mapping from location to value, right? So for each location, there is a value. It's a memory in the sequentially consistent semantics. On the other hand, promising semantics has a multivalued memory. Basically, it tracks the history of all the writes that is performed to the memory. So the reason is that we want to allow what is called a load hoisting. That means that a later loads should be able to be reordered so that the later loads can be executed before an earlier instructions. So in order to model this, instead we are going to have a multivalued memory that tracks all the history of the execution, and then the load to read from an old value, so that effectively allows the models the load hoisting. So I will show you the example of this later. So let me be more concrete about this idea at the later slides. The second idea of promising semantics is what is called memory adjacency for modeling read, modify, write instructions. So as we discussed in the previous lecture, read, modify, write instructions should be exclusive with each other. For example, in the implementation of the acquire function of a spin lock, we said that, oh, if there are two threads that is trying to acquire a single lock, then we need to make sure that only one of them has successfully acquired the lock. That means that we need to somehow order the acquire attempts and allows only one of them to succeed in read, modify, write instructions. So in order to allow only one of them to succeed it, we somehow need to constrain the behavior of this read, modify, write, and memory adjacency is a way of constraining such behaviors. So for this, I will also show you examples later, so please wait a little bit more about this. The third idea is what is called views. In order to model possible orderings and possible relaxed behaviors in the promising semantics. So it is basically constraining a thread's behavior, constraining relaxed behaviors, constraining orderings, reorderings, basically. And this is also a concrete content in the later slides. And the last idea is promises that also inspired the name of this semantics, promising semantics. And this is in order to model what is called store hoisting. So recall that load hoisting is reordering a later loads to earlier. Store hoisting is similar. It is reordering a later store to earlier. So in other words, we want to speculatively execute a later store even before reaching the even before the program counter reaches to the store. So in order to model this, we are going to let the thread to promise to store to a value. Then later make sure that the thread will keep the promise. So that it also has some technical content and how to model these promises precisely, and I will show you in a later slide. So overall, these four ideas are forming a single semantics that is called promising semantics, and it will precisely describe what is allowed and what is disallowed in a concurrent program. So which behavior is allowed and which behavior is disallowed. It is defined by this promising semantics. So and one important notice that this is not actually what is actually happening in the hardware. In the hardware, there is a lot of optimizations inside microarchitecture, and these optimizations are very much different from the internal working of this promising semantics. Promising semantics is just a modeling of such relaxed behaviors. So it is modeling in the sense that this internal working of this promising semantics is not actually executed, but it is proven that it is enveloping what is actually happening in the hardware and compilers. So in that sense, it is just a model. But the purpose of a model is that it allows the programmers to more easily reason about the program. So the purpose of this promising semantics is letting users to reason about the concurrent programs on this semantics, which is presumably simpler than the hardware semantics. So yeah, that's basically the purpose of this promising semantics. And I will explain the ideas one at a time. And the first idea to explain is the multivalued memory. So let me show you a slide for this. So So yeah, in this semantics, memory is no longer just a simple mapping from location to value. It is a mapping from location to a list of what is called messages. A message is consisting of a value and a timestamp. Timestamp is basically a counter. Counter means that you're going to have a value that represents the time of at the time of this writing of this message. And the thread may read an old value from a location. As I said, in order to model load hoisting, we want to allow a thread to read from an old value, old messages basically. So let me show you this example. Load hoisting is here. In the left thread, x equals 1 is executed, and then r is read. In the right thread, y equals 1 is executed, and then x is read. So the behavior in question is whether r1 equals r2 equals 0 is possible. So in order for this to happen, this r1 should read from an initial value, which has not been overwritten by this write. And r2 is also reading from the initial value that has not been overwritten by this write. So how is it possible? So note that this is impossible in sequentially consistent semantics because either x equals 1 or y equals 1 should be executed first. And if it is the case, then R2 or R1 should be 1. So this behavior is impossible in sequentially consistent semantics, but actually it should be allowed in reasonable concurrent semantics because of the reorderings. These two threads are possible to be reordered. The x equals 1 and r1 equals y can be reordered because they are accessing different locations and there is no dependency between them. And same for the right thread as well. So we want to allow this behavior. So how to do this? So this multi-valued memory actually allows us to use this. So let's execute this program and result in how to manage to exhibit this behavior in this program. Okay, at the beginning, we want to execute the left thread and executing x equals 1. And at this point, we want to insert a message to the memory. So record that for each location there is a list of messages, and when x equals 1 is executed, we are going to insert a message. Its value should be 1 because 1 is written. And for timestamp, we are going to choose anything. So we are going to just choose this. So the actual value is not actually that very much important. Let's say it is 5. At timestamp 5, we are going to write x equals 1. And so far, so good. And we are also executing the y equals 1. So, and similarly, we are going to insert a message to the location y. And this message value should be 1 because 1 is written at this instruction. And you're also going to choose a timestamp at your wish. For example, it can be 7 or 8. So note that the timestamps of the different locations are very much different. So this one and this one is not compared. So they are in a different space, namespace of timestamps. So even though this is 5 and this is 8 in timestamps, they are not compared. It is nonsense to say that this is before this. So in the same location, they are ordered. 0 is before 1 because they are in the same namespace of timestamps. But comparing this one and this one, or comparing this 0 and this one is not that important. It is just different. Okay, so far so good. We wrote 1 to both x and y and appended a message to each location. And now we are going to execute these reading instructions. So in the left thread, we are going to raise 0 from y. So effectively, we are reading this message instead of the latest message that contains the value 1. It is specifically allowed in promising semantics because a thread can read an old value that is not overwritten by that may be overwritten by latest writes because the information is tracked in the memory. 0 is there in the memory, so we can read it from the left thread. Similarly, we can read from x in the right thread because 0 is there. Even though there is a latest message that is more recent than the value 0, but that's okay. We are anyway going to read 0 from the memory. Even if it is old, it is there in the memory, so we can read it. So this basically allows load hoisting, reading from an old value, or loads are hoisted across an earlier instruction. So it is the same thing, but represented in a different flavor. Anyway, we are going to able to read 0 for both reading instructions in this single example, in a single execution. So this basically allows load hoisting. Okay, this is the first idea of promising semantics, multi-valued memory. And I'd like to proceed to the second key idea, which is memory adjacency. Okay, so far so good. But there is another example that is a counter, which is that, if the left thread and the right thread are performing a read modify write, for example, fetch and add, so it should be the case that they read different values. So it is impossible for R1 and R2 be 0 at the same time because they are atomically increasing the underlying value. Right? So it is a purpose of this read modify write or update or this fetch and add. So we need to somehow constrain the behavior of the threads in such a way that reading 0 for both threads is not happening. So in order to model this idea, so we have to adjust the message a little bit. In order to express this idea, we are going to say that message is no longer a pair of value and a single timestamp, but it is a pair of value and a timestamp range. So it has a volume now. So volume means that it is no longer at a single timestamp, for example 5, but it is occupying, for example, timestamp from 5 to 10 or 5 to 8. And why we do this? We are going to do this because we want to model read modify write in this way. So in order to append a message that is the result of a read modify write, then we require that the new message is adjacent to the old one. Adjacency means there is no gap between the two messages. So they are now ranges, and we want to make sure that if a message is read modify write, then the two ranges of the previous and the current messages should be adjacent without gap. Okay, so it is enough explanation, and let me show you an example. In this example, the two threads are fetch and adding 1, and let's say that we want to execute the left thread first. And it can read 0 because there is a message that has a value 0. And now a message has a timestamp range, and let's say that it is from this to this. And the message should be 1 because you're atomically increasing the line value by 1, and the value was 0. The value 0 is atomically increased by 1, and the result is 1. Now, in the thread 2, it is also trying to fetch an at 1, but at this time it should read 1 because 0 cannot be updated once again because its adjacent position is already taken. So the right thread perspective, in order to perform a read modify write, it should be adjacent to only a single message. So only this one message can be read modify write, read and modified and written, and as a result, it should be this message should be appended after the 1. This cannot be appended before right after the 0 message because this position is already taken. Instead, it is taking this position by incrementing the value 1 by 1. And the result should be 1 because the original value is 1. So in this example, we can see that, it cannot be possible that the R1 and R2 are the same at the same 0 at the same time because of the memory adjacency. So this basically models the exclusiveness of the method 0. Method 0 cannot be read, modified, and written by multiple instructions. So that is basically the essence of the RMWs, and this idea is captured by method adjacency in this semantics. Okay, so this is the idea too, and let me proceed on to the third idea, which is about views. A view is a little bit more difficult, and it is actually starting to describe the reorderings and relaxed behaviors. So the motivation here is that multivalued memory, which was the first key idea of the promising semantics, it allows too many unintended behaviors. So there is no constraint on the reason writes at all, except for those the memory adjacency for read modify write. The plain reason stores can arbitrarily read and write to any locations in any timestamp. But it is too much. It introduces too many unintended behaviors, and we need to constrain the behaviors somehow. And such a constraint includes what is called coherence or what is called synchronizations. So coherence means that, for example, if you read from the same location twice, and then the later reads should be somehow later. Somehow should read a later value than the previous one. So when a single thread executes the accesses to the same location, then the accesses should be somehow congruent with each other. They should respect the order. And the synchronization is already we discussed. We already discussed briefly about release, acquire, and fences, and these are acting as a synchronizer. If there is a release and there is an acquire, and they are executed as if they are executed in the same thread. So it introduces some constraint on the behavior of multiple threads, release, acquire, or fence. So they are modeled as synchronizations, and the synchronization is also represented with the views. So this is the motivation of the views, and let me tell you a little bit more about the mechanism of these views. So first things first, what is view? A view is mapping from location to the timestamp. So it is a definition in the promising semantics, and here are a few examples. The first example is a per thread view. For example, we said that this bright green is for thread 1 and this dark green is the thread 2, and each thread has a view for coherence. So this left thread's view has pointing to this message, that is value 1 for location X and value 0 for Y. That means that the thread has acknowledged the messages, this message and this message. So, and as a result, all the future accesses to the location X and Y should somehow be constrained by the knowledge. The knowledge is that I know the messages 1 and 0. The messages are propagated to me. So in the future, I should not access the overwritten values at all. So for example, if the view is at here, the thread 1 should not read the value 0 further, because it is already overwritten by 1, and this message 1 is propagated by myself. So it is not possible to read the old value. No longer possible. And also, there is a different kinds of view. Now, which is the second kind is a per message view for release acquire synchronization. And in order to model the release acquire synchronization, we need to somehow transfer the view from a single thread to another thread. So in order to do so, we are annotating a message with a view that is just released from the thread. So as a result, this view, the scarlet view, are annotated or fixed to this message. So this is represented as the message view. So I will tell you a little bit more about the detail of this, but here the key idea is just, there is a view that is picking a message for each location, and this view is somehow managed in order to order the behaviors and remove the too many relaxed behaviors. And the final kind of view is the global view for sequentially consistent synchronization. So there's an SC fence that is a very powerful fence, and it is globally synchronizing with all the other SC fence. And in order to model this, we need a global view, and there is also a view for SC synchronization. So I will tell you a little bit more about all these views in later slides. Okay, the first thing to do is modeling coherence with per thread views. So as I said in the previous slide, a per thread view is representing a thread's acknowledgement of messages. I am thread 1, and I have acknowledged the message 1 for X and message 0 for Y. And as a result, my view is like this. So acknowledgement means that I will never access an overwritten messages. So I will not access this X equals 0 because it is already overwritten by the message that I am pointing to. So that is basically the key constraint that is imposed on the behavior of a thread. And this models per location coherence. So let's see the examples. So in an RR coherence, 2 consecutive reads, this read and this read, should be ordered. Let me tell you a little bit more detail about this. Let's say that in a different thread, X equals 1 is executed. So as a result, there are 2 messages. The initial message that contains the value 0 and the message that contains value 1, because it is just written by this thread. So there are two messages, 0 and 1. And here we want to read 1 and 0. Is it possible? So I'm going to say it is impossible because 1 is more recent value and R2 should not be reading on old value that is already overwritten by this the earlier read. So let me tell you how to model this idea, how to model RR coherence or read-read coherence in the promising semantics. So at the time that R1 equals 0, R1 equals 1, by reading X equals 1, the thread view is updated to point to the value X equals 1. So the thread here is pointing to this message, X equals 1, right after this instruction, because this is value 1 is read here. And after that, we are going to read X again. And at this time, we cannot read 0 because X equals 1 is already acknowledged by the earlier instruction. And as a result, we cannot read an old value, and we should read the latest value 1 here, because 1 is not yet overwritten by myself, because I am pointing to this location, this message. So overall, this behavior is impossible due to the coherence and the per thread views. And R1, if R1 equals 1, R2 should be 1 at the same time. Now we are going to discuss RW coherence, which is here. It is going to read X and then write to X. And if it is the case, we have to know that, this R equals X, it should read 0. It should not read from the later write. It should not be 1 that is written by this. So that is basically the RW coherence or read-write coherence. If there is a read and a later write, then they should be somehow ordered. How to model this? So when you read the value here, you are effectively acknowledging the message. So let's say that the view is like here. Then we mandate that a write should be written, the message should be written beyond the current view of the thread. So if the view is here, the message should be put here. Here, it doesn't matter. But it cannot be put in here because this area is already overwritten by the current message here. So if you just read it, and then the write should happen later. So that is the rule of read and write for this RW coherence. As a result, when you read a message, then the message cannot be what is written later, because this message should be written after the timestamp of this read. So as a result, in this example, reading 1 here is impossible. So similarly or dually, there is a write-read coherence or WR coherence, which means that if there's a write and then read, and then it should not be reading an old value that is overwritten by this. The same thing. By writing 1 to X, the person view is at this point, for example, and as a result, we cannot read from an earlier message. 0 is already overwritten by this message, so as a result, this should be reading 1 instead of 0. There is also write-write coherence or WW coherence, and if there is a 2 writes, X equals 1 and X equals 2, and it should be the case that at the end of the day, the memory contains the messages 1 and 2, and they should be ordered. 1 is before and 2 is after. The reason is the same. By writing X equals 1, your per thread view is at this point, And after this, you have to write the message, and the message should be placed here because the preset view is here, and you can write anywhere you want as far as it is after the preset view, but not here. Here is already overwritten by this message, so this cannot be placed with a new message that is due to this x equals 2. So to summarize, there are coherence, and in order to model these kinds of coherences, we manage the post-thread view and reads and writes. All the accesses should happen after the current thread's post-thread view. So read-write, regardless of whether the access is read or write, it should happen after the current thread's view. If the thread view is here, then you should read this message or later messages if there is one. And if the view is here, then you should write new messages later. On the other hand, reading and writing changes the current thread's view. So if y's view is here, then the thread is reading this message, y equals 1. Then the view is updated. It is no longer pointing to this. After execution, it is now pointing to this message. So the view is also changed, and the view constrains the future behaviors. So it is intertwined with the execution of a thread, effectively reducing, taming the relaxed behaviors and ordering instructions when necessary. So this is the views, and this is a visualization. When your view is here, then this area is readable and writable. This area is already overwritten, so you should not access the locations. Okay, and there are third example of the views. Second example of the views, which is a per message view. The per message view is representing the view at the time of a release write. So if a view is released, then the view is annotated with the corresponding message, which can later be acquired by another thread. So it is basically for modeling release acquire synchronization. Here is an example. This example is already explained a little bit in the previous slide. X equals 1 and y equals 1, but with a release. In the right thread, y is read, and if is 1, we want to assert that x equals 1. Here, the load here is acquire, and the store is a release, and as a result, there is a release acquire synchronization. So that's the reason why this thread should read x equals 1. It cannot read the old message because there is a release acquire, and x equals 1 should be propagated to the second thread at this time. So that's the reason why the assertion should succeed. And in order for this access to succeed, we somehow need to model or transfer the view from the first thread to the second thread. And it is still with this release acquire synchronization. I will tell you a little bit more about this. So in order to see whether this is actually assertion actually is guaranteed, we are going to execute it. At the beginning, we are going to execute x equals 1, creating a new message x equals 1 here. So far so good. There is no difficult things to discuss for now. And then now we are going to execute y equals 1, but with a release. How to do this? We are first incrementing the first thread view. So it is now x equals 1 and y equals 1 because it has just written the new message, so the first thread view is updated. And at the time of the writing, it is a release, and as a result, the new message that is written here should be annotated with the view at the time of this release. So at the time of this release, the first view becomes this. Because the x equals 1 is already written here and y equals 1 is just written. So the first view is here, and this first view is annotated with the message as a proof that, oh, this view is released at the time. And now, in the second thread, it is acquire loading the value 1. And it is going to read this message, but it is acquire. So what it does is that the per message view here, annotated here, is incorporated into the per thread view of the right thread. And as a result, the right thread's view becomes this. So recall that if this is not acquire, then the view should be x equals 1, x equals 0 and y equals 1. Because it is not acquire. If it is not acquire, then only the view for y is updated. However, it is acquire in this example. And as a result, the per message view is incorporated into the per thread view. And as a result, the second thread's per thread view, which is represented as the dark green, it is updated to point to x equals 1 and y equals 1. That happens to be the same with the per message view. So as a result, this assertion should succeed because the view is here, and this old message cannot be read by the thread. So the moral of the story is that we want to transfer the per thread view of the left thread to the right thread. So as a messenger, we are going to annotate the message with the per message view, and we are going to annotate the per thread view of the left thread to the message, and this view is incorporated into the right thread. And effectively, the knowledge that x equals 1 is written in this message, that knowledge is transferred from this to this, from left to right. So this assertion should succeed. So that is basically the idea for modeling this synchronization with views. So here is the last example. So here's the last example. That means that is almost the same example here. So x equals 1, y equals 1. Y is red and x is red. The same. X is written, y is written, y is red and x is red. But instead of annotating with release and acquire, they are annotated with relaxed. That means that there is no ordering between with other instructions. Instead, there is an active fence. Active fence is a very strong fence that separates all the instructions before and after this fence. And as a result, similar to the previous example, x equals 1 and y equals 1 should be separated. And this load is separated. And this assertion should not fail thanks to the strong ordering among the instructions. How to do this? How to model this behavior? How to forbid this behavior in our model? So that is basically the question, and that is by maintaining a global view for SC synchronization. So let me execute again. If this is executed before, the right thread is executed first, then y should be 0 because there is no message that is different from the value 0. So nothing happens. So assertion is automatically uh, uh, asserted because it is not executed at all. So we need to execute the first thread first. So x equals 1 is appended to the memory, and the view is updated. Per thread view is updated. And then we're going to execute an SCFence. And at the time, we are going to update the SC view with the per thread view. So SC view is incremented to the per thread view of the left thread. So that is the internal working of this. And then y equals 1 is executed. That means the per thread view of this one, y, is updated to point to 1. So the crucial step here is the SC view. This SC view is it represents the per thread view of this left thread at the time that this fence is executed. At the time that this fence is executed, only x equals 1 is executed, and as a result, x equals 1 is written here, and this view is pointing to x equals 1. Now, in the right thread, it is reading y equals 1, updating its per thread view to point to y equals 1 here, and then execute an SCFence. And this time, what is interesting is that, there are two things that happen. The first thing is that I am also updating the SC view. I am acknowledging this message and this message, and this is incorporated into the SC view. And the other effect is that, SC view already has this view, so my view is updated. My view is updated to from x equals 0 to x equals 1 because the SC view is executed, and I need to acknowledge what is already annotated with SC view. So the view becomes this. So okay, let me explain again. My per thread view is here, x equals 0 and y equals 1. But it should be updated with my SC view. And as a result, this x equals 1 is automatically acknowledged at the time that fence is executed. This is very much expected because this x equals 1 should be acknowledged here by the fact that it is executed before this fence, and this is executed before this fence, and this is executed before the assertion. So the per thread view should be updated to point to x equals 1 at this point. On the other hand, as we discussed, y equals 1, it should be released to this SC view because a later fence may also synchronize with me. And as a result, all the knowledge that is before the fence should be transferred to the SC view. And as a result, my per thread view and SC view are updated to the join of the two views. The join of the two views is x equals 1 and y equals 1. And as a result, my view and the SC view becomes the x equals 1 and y equals 1. And automatically, the assertion is safe. So this is basically the key idea of the views, and this is explaining various things. So for example, synchronization and coherence. And there are two kinds of synchronization: reverse-acquired synchronization and SC synchronization that we learned in the previous lecture. So today we are going to stop here. And we are in the next lecture, we are going to study the last idea of promises semantics, which is promises.